to unified conferencing.
Did you take my seat? Soul sitting? No, he's like...
Shift the camera. You move the camera left a bit. Can you shift the camera again?
Okay, it's time. So today we have a lot to cover, and it is the eve of the midterm, so to speak, because Monday, I guess, is the midterm, right? I'm really excited about this midterm. It should be really good. I think you're going to like it. As we did in 2017, we'll have an intermission. We'll serve snacks. The coffee machine will be here. Maybe even some energy drinks. And I have authorization from the president's office to use one of the conference rooms as a chapel, if you need that too. Anyway, it'll be fun. You'll really enjoy it. So today we're going to cover case studies and then get into naphthyridines, which are the most vexing of the heterocycles we have seen so far. And you see these a lot. I would bet a lot of money that at least one of you in this room will one day go on and make naphthyridines as part of your project. Patrick, have you made naphthyridines yet?
I haven't made any, but I've seen them.
Yeah, they're all over the place. So, hopefully today it will become clear the order of events that these lectures were given to you, why they were strategically chosen the way they were. Anyway, we need to finish up what we talked about last time, and as a good introduction to naphthyridines, before we get into them, this natural product, which is on the front page of the handout, maybe we can display it on the board there, amphimedine, was made by Stille, Nakahara, and Prager by very different approaches. And so the Stille approach, and basically also the Nakahara approach, relies upon a late-stage stitching of the naphthyridine ring through a simple cyclization event that takes place here. So we made our first key retrosynthetic disconnection. Stille then moves on and uses an azidyne Diels-Alder onto that quinone linked to a pyridine. And then we need a key disconnection here, keeping in mind that it is, of course, Stille as the author of this paper. So when you see this pyridine connected to a quinone, what's something you can do to get rid of the quinone? Zhang, any thoughts here? So we don't want to carry a quinone through many, many steps. We pretty much want to unveil it right before the Diels-Alder. Is there a good equivalent to that?
Like the diphenol.
Diphenol or dimethoxy is just as good? Sure. And then since this is Stille, we're probably going to want to remove that through a Stille. And we know how to make that, don't we? I mean, we just learned it yesterday. So, Cheng, why don't you give us the route to make that compound? Friedlander where? Well, but, in order to do the Friedlander, so if we make that disconnection, it's going to end up at something that looks like this. Correct? Yes. And even if you were to get simple acetaldehyde, which we talked about yesterday is probably not a good Friedlander substrate, even if you were to get that to go in, you're missing your functionalization here. When you see this unit, really, remember, it's a keying element for that, correct? Just treat that with triflic anhydride, you'll get the corresponding triflate. And then we learned 1,000 ways of making that yesterday. And hopefully someone from the quinoline team, Vince or Hannah, can just refresh our memory really quick. What's my starting material? 1,3-dicarbonyl, or you can say you could just make this intermediate that we saw, and this comes in C2 from the corresponding amine plus alpha beta unsaturated compound by Friedel-Crafts. Right, this connection needs to be near instantaneous for you guys. Or
the camps here.
Camps, fine. That would require we'll give it to you. And then just heat with acid. So Nakahara said, I want a palladium-free approach. And you should be able to make this compound through a palladium-free approach. Like, why do we need palladium to put that arine in there if we're not doing medchem? So we could do exactly what we did yesterday at the very beginning of the lecture. Take the same ArNH2 and use as our ketone partner Ar here. Right? Same compound. No palladium. That's what Nakahara did. Otherwise, exactly the same route. Max, are you comfortable with that?
Wait, maybe I'm wrong about the oxidation.
Yeah, the esters in the wrong oxidation state.
Esters in the wrong oxidation state.
Because that ester is becoming what's currently labeled as 1.
Oh, no. Oh, yeah, okay, right, great. I mean, you can burn that off really easily just with POCl3 and then palladium, or you can just... Sorry?
And it's not palladium free anymore.
So that's... but you don't even need palladium to remove the chloride. You can use borohydride. But anyway, this will give you the right oxidation state. Yeah, thanks, Max. You see, it's good. If I look for confusing looks, then I know that I probably screwed up. Okay, great. Any other questions on these two approaches? Okay. The Prager approach is very different. Super weird. And it starts with this fluorinone, which before we go on further to understand what happens, how he manipulates that fluorinone to the product, maybe we should think about how you make the fluorinone. So we can think about the different disconnections here. There's that bridging ketone in the middle. So it might make sense to make a disconnection in that general vicinity, but you may have other ones that are better.
Should we carbonyl cross coupling?
So which bonds do you want to break? Carbonyl cross
So
couple?
just breaking ring D.
Into what components?
I guess by arrow between the pyridone and just the arrow group. And plus the appropriate functional handles for that. So like a halide there. And then we'd probably do another halide on the pyridone in a reductive fashion.
And then just palladium CO and hope for the best. Okay. How do you make that? Got a lot of halogens there. It's going to make your cross-coupling life to put that together a little bit troubling.
Well, maybe if X were like nitrile or something, we can go back to like a...
Let's do that, Max. If X is a nitrile, you've already got your carbonylation. So why do you need to do carbonylation again?
Oh, you don't. It'll just a knee-jerk response.
What can X be here?
Just some chronically file. Like,
How about we just remove it?
oh, sure. Okay, freedom grabs, yeah. Fair enough, yeah.
Is this a signaling element for a type of reaction?
Yeah, for expression sense, right? Yeah.
They did it this way, but it's no problem if you propose on paper, this is OET and this is NH2. The canonical Gorashi-Thorpe would be that. That's what we learned at the end of class yesterday. So, but they actually took this independent enamide, or enamine, and then coupled it with that. But you can easily draw this on paper, the opposite polarity. It's fine. I'm just showing you what they did. But what we should draw based on yesterday's lecture is the regular Gorashi-Thorpe.
What specifically do you see as a key element for the Gorashi-Thorpe?
Always this. Pyridone, cyano, it's instantaneous Gorashi-Thorpe. Once you see that, you look for how do you derive it from acetamide, cyanoacetamide. That's what you should be thinking about. Okay, so they made the fluorinone. They take that fluorinone, they treat it with TMS chloride triethylamine. That protects the pyridone, because if we don't protect the pyridone and we add in our organometallic reagent, it's just going to deprotonate, and you can never add to that ketone. It's game over. So in situ protection with TMS chloride at the pyridone NH. Then you add your lithiate reagent in. You get your tertiary alcohol, and that sets the stage for problem of the day number 9. That Tucker has kindly volunteered for. So they'll pass you the iPad very close, and I will basically mimic whatever you draw up there. You like eliminating alcohol? Okay, good. Polyphosphoric acid, pretty strong acid. All right. Got a nucleophile on there, luckily. Yeah, don't worry about filling in all the substituents. Good. That's fine. Don't need to worry about what it's there. Yeah. All right, great. You go ahead and add that in, and I'll help you by adding it in here too. Resonance form, or whichever one you like. This one's better for you. Whatever one you like. Both work fine. You don't need a nitrine, but if you want to draw a nitrine, we can get that product.
You can do a lot of things from a nitrine.
If you, I mean, if you want to draw the nitrine, it will still get you to product because the arrows are going to be the same. If it helps you can look at this, the handout for what the structure of the natural product is to remind you. Aha.
Okay. We get shift of
Yes.
this carbon-carbon bond.
Which carbon-carbon bond? Let's look at your paper here. Which one? Got A, B, C. A sounds good. And if we redraw that, we get that. Great. And that kind of makes sense because the migratory aptitude of that phenyl is going to be the best. Best able to stabilize cationic character in the transition state. So that's why A moves. Perfect. Thanks, Tucker. All right, great. So when we treat this with POCl3, what happens, Tanner?
You're going to chlorinate the ketone.
POCl3 does that. Methyl triflate? Steve?
Methylase superior.
Which one?
That one. Yeah.
Because?
Sterics.
KOH and potassium ferrocyanide. An old school way of oxidizing the pyridinium salt, Van Tamerlan uses to make cytosine as well, to the corresponding pyridone. So that gives us this compound. And then when we treat this with copper cyanide, DMSO, and heat, this turns into the cyano and polyphosphoric acid. Look at the structure of the natural product. Does our final closure. Do you see it? There's our cyano. It's right there. And there's our closure, right here. With PPA. Loss of ammonia after cyclization. You see that? Yes? Good. Pretty sneaky. Okay, great. Before we go on to the grueling case studies of today, it's important just to cover one other tactic that's used quite often in quinolone synthesis. This one comes from Pfizer, well before Patrick's days there. But this is an OPRD precedent. And so they make this quinolone via ring closure of the type we learned yesterday. And this is derived from this very bizarre benz-isoxazole. And this benz-isoxazole can be reductively opened using titanium trichloride. And that is made through problem of the day number 10. The last problem of the day. And problem of the day number 10 involves taking an aryl benzonitrile and some base and methanol. And happy for someone to take the iPad or simply make me the chalk slave. Deng, you seem interested in making me do your bidding with the board here.
So I think it deprotonates first.
All right, I'll do that for you. Now, what do you want me to do?
Probably adds in ortho to the nitro. And then get a negative charge next to the nitro.
And now, what do you want me to do?
Does one of the oxygen condense onto nitro?
What do you mean by condense? You want it to add into the CN bond,
Yeah.
or
Possibly.
Saying, look at how many carbons you have in the final natural product of the metal product relative to the starting material.
Yeah, I was thinking something along the lines of like decarboxylating, but
all right. So that's your intermediate you would get if you add into nitrile. Can we get home from there?
maybe, maybe not. I was thinking you can possibly decarboxylate, like imagine the new like amide bond is like converted to a ketone or a lactone and then decarboxylates.
And then it
Or maybe it goes through like
a quinomethide type.
yeah.
Okay, so a quinomethide type, if that were to happen, one could imagine, the net process maybe is an elimination of HCN to give you that, perhaps,
Yeah.
would give you the intermediate you want, and then
Yeah.
we could add in. Or perhaps it does just a pedestrian SN2. Either one is fine. They posit that it is just an SN2. But now you look, we've got our ring system.
Yes.
We're in methanol.
So I guess the methanol adds in to the amine. I'm still trying to think.
We can certainly do that. There is nothing wrong with what you said. And my point of doing whatever you say is that I can get to the product almost no matter what you say. This is the adduct you recommend, right? There's no problem with it. Now what? Get me from here to here.
Oh, maybe I didn't need to add any methanol. Does the oxygen just kick down to kick out like the alkoxide?
This oxygen kick in?
Or oh no, from the ring, from the heterocycle.
This one kick in?
The third one.
This guy.
Yeah. And then kicks out the.
There's nothing to kick out. If you you want to break this bond?
Break the NO bond, the NOH bond. Like,
Oh, yeah. So we can lose a proton. Well, the first thing you need to do is get rid of the methanol,
yeah.
right? So
Yeah,
let's get rid of the
that's
methanol.
yeah.
That gives us this species. And now we lose our water.
Yeah.
You've got base around. This is a very acidic proton. And you're done. We could have just gone from here straight to here.
Can we see the board on the larger screen, please?
There was no need for the methanol detour,
Yeah, that's true.
right? But you got us there, nevertheless. No problem. So we can go from here directly to here, lose water, and we get our benz-isoxazole. The beauty of this is that we take advantage of the innate reactivity of the nitro. It incorporates the arene without any cross-coupling. The opening gives us an array of functional groups now that sets the stage beautifully for a Combs-type cyclization. Combs, or maybe a different name reaction. But the bottom line is you just make your acetamide there and then treat it with base and you're done. Remember that disconnection? Okay, that was the last mechanism we were going to cover today. The rest of this class is going to be all about strategery. When do we make certain things and how do we make them? It's basically all about informed sci-findering. All of you can just take the final compound that you're faced with and go on sci-finder. Of course you can do that. But anybody can do that. If you want to beat them in the race, you've got to make a disconnection that makes the most sense and then go and look for that particular building block. So problem today number 11 we'll do as a group. And pretty much for the rest of this lecture, we're going to be analyzing these bicyclic aromatics, heteroaromatics, and determining the most logical ways to proceed. Which heterocycles do we make? How do we break these down to their first principles components? So for these first two, A and B, we need to harken back to the Thiophene notes. And we need to go back to our pyridine and quinoline notes to determine how we proceed. So just based on your instinct, Dongmin, would you like to break A and make a B, or would you like to break B and make an A?
I would break.
So the first strategy Dongmin is saying is he's saying we're going to go in the forward sense from A into B. Is that correct?
Yeah.
And that would require what substituents?
Chlorine on the two conditions. Again,
And then a decarboxylation, right? Jess, do you like it?
No.
Why not?
The previous
It's
two.
pretty understated. Because why?
Because you need to synthesize the pyridine. So basically,
You don't want to synthesize the pyridine?
I mean, then you break two rings. If you break ring A, then you can find one at least.
So you're suggesting to make B and annulate on A.
Yeah.
And so what is the starting material for, if we do that, we need a thiophene building block. What is your thiophene building block?
The two amino
And how do I annulate that?
with the diketo 1,3.
What do you think, Don?
yeah, just wait.
Do you have a preference?
Yeah, now, I think now maybe synthesizing the pyridine is better.
You think synthesizing the pyridine is better?
I mean,
Annulating
Yeah.
onto that by making the pyridine versus you're still going to need to make it here. But just from a strategic perspective, if you look at these two disconnections, is this a whole lot simpler than this? Not so much. It's not a huge...
Can you make Dongmen's purity with the cyanamide?
Sure.
So if you draw the pure
So
cyanamide,
this one comes from... It's a great exercise that you've got us to embark on here, Tanner. And that's just Guareschi Thorpe. Great. But I have to do one step to make that. Then I've got to do a POCl3. Then I've got to do a diball. Then I've got to add this in. Then I've got to decarboxylate. Versus starting from coconuts on an island and mixing these two together and getting the product. Right? So, you know, if you put this on a midterm, we can't mark it wrong. But when you get a job, right, your bonus could depend on it. Okay, how about B? Same type of logic. So, Steve, what do you want to do? Do you want to annulate on A or annulate on B?
I think we should probably try to emulate on A. The pyridine seems
So you would like to take B and put A on there. And how would you like to do that? I need to put, I don't know, something here or here.
Can we use like the innate reactivity of the 2 position of the furan to attack carbonyl?
Intermolecularly or intramolecular? Or what do you mean?
Inter.
So what, you want to put some carbonyl here? What's the immediate precursor to this?
Can you draw the 1,3-dicarbonyl for me from A? Or sorry, to
There's really not a 1,3-dicarbonyl.
1,4. Fine, 1,5. We'll get there.
This. That's their 1,5-dicarbonyl. That would lead to that pyridine. Is that what you're talking about?
I was thinking about going the other way around. So the 3 from the sulfur, and then
What's the 3 from the sulfur?
make that a carbonyl.
Here a carbonyl?
Sorry, no, the. So the 4 position of the heterocycle make a carbonyl, and then what is it?
Which one?
And then the 7. Okay, so. So if you
I need a
if you
GPS.
take the heterocycle, the other one, the one on the left, 4 and 7, turn those carbons into carbonyls.
5, 6.
Okay, 5, 6,
Yeah.
5 and 7.
Okay. Okay. Okay, got it. You mean this? Is that what you're talking about?
Yeah, more
All
or
right.
less. And so if you disconnect the 2 position,
But how do I go from here to here?
so if you make the aldehyde at the 2 position, then you'll have an alcohol, and then treatment with POCl3 and cross coupling the pyridone should give you the methyl, and then I think you just need one more oxidation. Or actually, no, I think that gives it to you, right?
So you're saying start here with a methyl Grignard addition to an aldehyde?
No, I was thinking using the 2 position of the furan to add into an aldehyde.
Oh, I see. You're doing a Friedel-Crafts.
Yeah, basically.
Okay. So let's do a Friedel-Crafts, Steve. Would you agree this is a pretty acceptable disconnection? That's B to A. How do we make this building block? So you're taking advantage of exactly what you said, the innate reactivity of the 2 position, not the 7 nor the 90, but the 2. And that leads us to a simple building block. And how do you go from here to here? Well, you could do a Henry reaction, reduce and acetylate. That'll work. How about the let's make a pyridine and annulate on a thiophene? If we use Dungman's logic again, it leads us to that, right? And then we do a Feiselman type, add in, and then reduce the acid all the way down to the methyl. But we got to make that beast. So you need some thought to think about that one. You probably need to do some lithiation, some cross-coupling. Maybe you'll start with the 1,5-dicarbonyl, but then if you do that, it's hard to imagine how you get the aldehyde here and not here. You're going to have some selectivity issues. Like when you get into the nitty-gritty of how do you make this darn thing, because we put an ethyl here and a methyl there, that really screws things up. If it was methyl-methyl, it might be easier. So you go down that analysis and you realize, okay, the thiophene is the one. And then if you go through the aromaticity analysis, thiophene and pyridine, are one of those ones that are pretty close, and it depends on the substituents. So you can't use that argument either. Okay, great. How about C? Bless you. I'm worried because there's so many positions we can number on this one. But why don't we just do it by ring lettering? And all I'm looking for here is your instinct on where to cut.
I'm sorry. So what were you going to say?
The same thing.
Yeah. Ring C through C3 at the middle.
Oh, actually, no.
Oh, great. So we're going to have 2. So, Max, you want to break there. Is that what you just said?
Yeah.
And just Bishop-Niporowski it closed?
Yeah.
Great. How do we make that thing?
Maybe the
Oh, sorry, what happened, Tanner?
Missing a nitrogen on the
I'm missing a nitrogen. Oh, sorry, thanks. Doesn't change what we're doing, but yeah. Great. And how do you make that?
Depending on what you can buy, maybe you can cross-couple just onto the bromine.
Yeah. Okay. So if you get lucky, well, first thing you'll realize is that nitration of quinoline, isoquinoline, goes selectively here first. So you would find that out pretty quickly because when you look for the vendors for the nitro or the amino, you'd find there's 150. So that's where you start sci-fi doing. And then you'd say, okay, how do I put a bromo in the ortho position? Probably NBS would give you some good selectivity. And then you would take your C2 protected boronic acid of indole, cross-couple, and then acetylate. Or you could even go in with the acetylated compound and just work it up with. So yeah, that's a cross-coupling route that will get you there. Saul, you had a different disconnection?
It gets you to more or less the same place. I was just have the acetyl on the indole, still break ring C, but break the CN bond and the C2 bond of the indole.
Oh.
But it gets you to the same place.
Well, that's interesting, because if you break that one, You mean this.
Yes.
Is that right? And how do you close that ring?
And you need some functional handle. It's
So maybe we could use the same bromo?
Yeah.
Or there is, at least for academic or process possibilities, you might be able to think about a formal 6-pi. Sometimes these things will actually do 6-pi closure, and then with an oxidant, they will aromatize. So not something you want to propose to a medicinal chemist. But a process chemist may like a suggestion like that. What if we just get, sorry, question?
Phil, in the first approach, at the cyclization step, will we have the reduced selectivity issues because of NH of indole?
The C3 position is always the more nucleophilic in a Friedel-Crafts type cyclization, so you wouldn't have to worry about that. Never going to add in. And if it did, it's reversible. That one just adds back. You just would close back out, and then only C3 is irreversible. It's a good question. So yeah, when you have an indole and you're doing Friedel-Crafts, it acylates here.
But it's heterocyclization shouldn't be reversible once it closed.
Well, if you treated this with, let's say you did it under acidic conditions. If you did it like with PPA, then you can imagine under those conditions, the N would also, if you add it in, it would also add back out. But you should think that under acidic conditions, the nucleophilic part of the indole is C3 or C2, not the nitrogen. Unless you treat it with sodium hydride, then we're talking about nitrogen. No sodium hydride, no nitrogen. And if you treat it with a Grignard reagent, then you make it even more C3 reactive. It's a good way to activate an indole at C3 even more. Is treat it with a Grignard. You make the magnesium salt, and it'll go at C3. It'll alkylate there. It's a good question. So another way to think about this would be, what if we just annulated on the indole from a species like this? This is not necessarily the right answer. It's just another possibility you could have proposed that would have been just fine. We could take that compound, we could treat it with POCl3. And then we need a suitable nucleophile. That we can add in. So we could perhaps add in cyclohexylhydrazine, do a 3,3 followed by aromatization. It probably would also work with the phenylhydrazine, wouldn't doubt it. You might also just try adding that in, followed by an intramolecular. Heck, all good disconnections. No problem proposing any of those. How do you make this thing? Well, it comes from yesterday's lecture, right? And look where we are. Back to Max's starting material. All roads would lead you back to there. Questions? All right, Hannah, I need help on this one. So give me just the first disconnection as a med chemist. Let's simplify it right off the bat. Let's get rid of that. Great. And let's just focus on this compound. Do you mean the Dongmin disconnection?
Sure.
You mean this?
Yes.
And then decarboxylate somehow? Yeah. I see no problem with that. If you look that up, it's probably readily available. No problem. But what happens if you can't find that compound? what would be our Thiophene starting material. So this is just fine. But we need optionality. If we're in process chemistry, maybe you'll want 2 groups. What do you say, Steve?
Could you do cyanoacetamide
Onto
onto 2 aldehyde furanate, or 2 aldehyde thiophenol?
this one?
Yeah.
And you want to add in
Yeah. Yep.
this?
Yep.
And help me understand, if I map the carbons on, where's my cyano?
Yeah, you decarboxylate it.
And where are my other carbons? And how does my nitrogen get attached here?
Put a chloro there.
Oh, now I'm putting a chlorine here. Okay.
That should work right.
You're doing like SNAR onto a thiophene.
With a really crappy nucleophile. Let me ask you this question, and here's a good trick for you if you're stuck on the test or in life. Why don't you just pretend the thiophene is this? How do you make this? Just go back to yesterday's lecture. How do you make this? What's one way? Didn't we learn how to make this? How do you make it?
Start with the pyridone. The middle one.
And what is it, Hannah?
I said buy it from Sigma.
Buy it from Sigma.
Start from ALN.
Yeah. You need the equivalent of something like we talked about yesterday. And in practice, what people often do, you see this reaction in the literature, it's kind of weird. We'll cover the mechanism of it after the midterm. People just use malic acid, and they treat it with H2SO4, and it's usually extremely high yielding to give an intermediate that's kind of like this. And it has the right oxidation state in it. So you take malic acid, H2SO4, you react it with this, it will give you that. Very high yield. Now, why did I take this detour?
So you start with the 3 aminothiophenes.
The only thing you need to do is check, is my regiochemistry going to be okay? And we know C2 should be better than C3. And then once you check that off the box, you can use the let's pretend thiophene was a benzene ring trick. So if you get frustrated in the test and you're like, I can't stand these heterocycles, just take it back to a basic one. Replace the benzene if it makes you feel more comfortable. And then go back in and replace the thiophene. Is that helpful? Questions?
That typically works when like the ring you're replacing is pretty aromatic.
Right. It has to be that. Right? I mean, so don't do that when we get to things like triazole pyrimidines. You won't be able to do that so well. It's going to be a little bit more difficult. But yeah, for some of these, you could use that kind of, replacement logic. It works sometimes, especially in one like this. Thiophene is often replaceable with benzene ring, logically. Questions? What do you say, Dungman?
I think our very first isomer is the thiol would not go for C3.
You just subterfuges your own route. It's actually that is a good point, and I should have recognized that. So yeah. So Dongman has a good point, which is the Feiselman is really the first step would work, but it's going to be difficult for that. The first step is going to be difficult because the sulfur is probably going to add in here, not here. This is not a reactive site, so yeah.
I mean, you can start with like the pyridine or something on that side.
Even then, that's not an electrophilic position. So you have to be careful on Feiselman. It's a good point. If Dungman didn't bring that out, that would have been an error forever emblazoned on this video. No, that's not going to work. I agree. Yeah, that's going to be problematic. I don't know how you get yourself out of that hole except to say maybe you could try some palladium. But you'd have to have this as something different. It might have to be NHR. So put an amine here as a placeholder, and then do a palladium coupling with some conditions, either Ullmann or a Buchwald type with a thiol nucleophile. Yeah, that's a good point. Yes. So you really do need that Thiophene disconnection, don't you? Glad we have two. All right, great. Other questions, concerns before we move topic completely? Okay, so we learned about quinolines, we learned about isoquinolines, you learned about pyridines, and so if we put it all together, we end up at finally real-world heterocycles. And in the real world, things get difficult. These are naphthyridines. They come in 6 different flavors, and they can be vexing, depending on the substitution pattern you have, can make for extremely difficult problems. Even in simplest form, some of these are really tough to come up with a great route for. So we'll cover examples of every single type of naphthyridine to try to get you ready. So let's take a look at this first example.
I like breaking the B ring, rightmost bonds.
Rightmost bond. What does that mean?
The bond between the malonate, so between 3 and 4. From a formal aniline type compound. And then we're going to break between 1 and 2 next.
Formaldehyde won't get you there, but trimethyl orthoformate. And then we make this how?
So direct metallation should for sure go to the
I guess it'll just be this for now, and then you'll...
yeah, cover. And then that's forming a pyridine.
On paper, it looks fine. Is there a faster way to do this? What do you say, Pavel? Faster way?
3 amino pyridine and Boc is lithiated in position 2.
You need to use kinetic conditions to get that to happen. Thermodynamically, it should go C4. Yep. So just changing the base. Kinetic should be C2. But it's something someone would ask in the room, and you'd have to sci-finder and make sure and find the right conditions, and you might get a mixture. So is there a better way that avoids any lithiations?
Something like the Weiler dianion make like philic enough to add into the 2 position of the pyridine if it's got like a chloral or a fluoro or something on it.
So you would like to take...
Basically just reverse the polarity of that signal. Just imagine.
Weiler dianion should add here onto that. Perhaps if it doesn't, if it doesn't form a charge transfer complex with the nitro. Is there an extra carbon?
Oh, I see your point.
Weiler dianion and carbon is not the desired product.
Oh, yeah, sorry. E, yikes. Yeah, we needed to add. Yeah, that's a problem. No, yeah, you'd have an extra carbon there. So you need an acyl anion, basically. Yeah. So no, we need another way, and it's very similar to the way we saw yesterday. Like, If you just remove that nitrogen, I think everything will become super easy for you to think about. So I'm curious why, Saul, you didn't have this disconnection and just heat it up with PPA. Why didn't you make that disconnection? Were you worried about something?
So now that you draw it, I'm worried about reaching chemistry.
Great. Good point. So if you check the literature, you will find that when there is an R group here, it always goes exclusively at this position. If you want to reverse the regiochemistry, you can often do that by making the N oxide. It will then switch it to here. And you may say, how are we supposed to know that? Well, you don't need to know that. What you would do is say, I'm going to pretend this is a benzene ring, and I'm going to pretend I need to make a quinolone. And you remember the quinolone notes that the common way of doing this is by making this intermediate and heating it up. You say, I make it a regioisomeric mixture, but let me check. Then you would go to SciFinder and find, wow, turns out these cyclizations always go next to nitrogen. That's the logical tree. I mean, that's the best you can do. And so did they, TAs email you last night with something? Do you guys have your phones with you? Yes. So I will display this. Well, this is a sort of new feature of this year's class. And let me see, how do I get this to be the... Can you guys see the screen up there? Or you can use your phone. I think patent law and patents in general are something that you folks are not exposed to much. And to be sure, before you started at Pfizer, Patrick, did you read the patent literature often and know exactly what was going on there? Any students that are extremely familiar, except for Saul, with the patent process and patent literature? Yeah, probably not. So heterocycles are actually a good spot to talk about patent law for just a few minutes because there's probably a non-zero number of people in this room who will go into patent law. And if you don't go into patent law, probably most of you will write a patent one day. And at that point, you'll have a lot of catching up to do to find out what's the deal with a patent. How does it work? How do you find out the crispy way to get the information from a patent? It's actually a convoluted and complicated process. So anyway, what does a patent do? What's it for? What's it for, Max?
Securing intellectual property.
Security intellectual. Does it mean that does it say you can make something?
Well, it says that you... What do you mean? Like,
Does it give you the right to make something?
not necessarily.
Not necessarily. It doesn't give you a right to make anything. All it says is you can't make it. It's about protecting, it's about fencing property off. So the way the process usually works is you have an invention. It's recorded in your notebook. It's why when you go to the companies, they make you sign the notebook. It's really important because that shows the priority of when the thing was invented. And you don't think about this until you go to a company. And then you file a provisional application. And the provisional application then goes to a patent board. And that goes through a long process because then judges or lawyers who work for the government will then say, this is not right, and decline it, or you need to change this or that. And that process may take, a while. But it gives you a 12-month period. It's kind of like a placeholder that allows you to stake a claim. And then the PCT application is the next one you do. And it's kind of like a version of a proxy for international coverage everywhere. Why do people do the PCT? Because it gains them up to about 30 months of protection. So the provisional is filed here. It's not very expensive to file a provisional. PCT is a little more expensive. But then during this 30-month process, you can keep adding claims and specifications to your final patent. So what is the anatomy of a patent? This is why I sent it to you yesterday. It covers the synthesis of compounds in the class of these 1,5 naphthyridines that we just talked about. It's only a 30-page patent. Some patents will be 1,000 pages. They'll be miserable to get through. So what's the anatomy of a patent? The first page is kind of important. It's the cover page. And the cover page is useful because if you go down and see the history of it, you'll find, by looking at the history, you will eventually find what the priority date is. So if you go here, you say the thing is filed in 2014. Now, if you don't know anything about patents, you may say, oh, well, I made my compound in 2013, and therefore this patent isn't valid. But if you look at the documents back here on the cover page, you'll see the original communication happened all the way in 2012. So you'd be out of luck. So what you want to do when you see a patent and you're in a company, check the covers page first to see what date are we talking about. And if they've scooped you, the next thing you'll want to do is figure out on the specification page, what do they actually cover? In the specifications, which is the meat, it's what is the thing useful for? How did we make it? All of that is here. The data on the utility, all of it's here. You see these are procedures, the procedures that just cover what we talked about in this 1.5 case study. And then finally, often people skip to the very end of the patent because they want to see the claims. You always go to the very end of the patent to find your claims. Here's your claim, and this is called a Marcus structure. So the claims usually, the first claim is the one that is the broadest. And as you go to the individual genus claims, the corollary claims, they become more and more narrow. And the process of getting a patent involves going back and forth to a board of judges and patent examiners who will say, this claim is not, you can't claim this broad because of this or that reason, or this is obvious or not. So to get your patent finally as a valid patent, there needs to be a judgment on, one, there's clear utility. You can't patent something and say, it's an anti-cancer agent, and just publish DMAP. And then all the pyridines surrounding that. Just say all pyridines and draw a Marcus structure like this. Say, cure cancer. And just file it from your garage. That's not enforceable, and you won't even get the patent because you haven't shown it's useful. The other thing is the novelty. If the literature shows, oh, there's already a bunch of pyridines that are anti-cancer compounds, there's nothing novel about that. Novelty is different than non-obvious. It may be novel, but it may be obvious based on prior art. So a person of skill in the art might say, well, it's obvious you could just do this or that, rendering what you think is novel as obvious. So it needs to be both novel and non-obvious. There's a difference between those two. It needs to have a written description. So if you just have in your patent a couple of procedures which are kind of, you don't show how to make a person of skill in the art, how to make the stuff, there's no written description. You need to have a written description. What does it do? Were there assays, biological assays show, yes, I not only conceived of the thing, I also described how it could be useful, and then finally I enabled it by showing people how they did it. That's why you have procedures in these. And patents can be written in a friendly manner, showing you ChemDraw schemes, but they can also be written in a very aggressive, angry manner. Some people will write patents and only use IUPAC for everything. And you may spend countless, I have many former students that will just spend 6 months doing patent stuff. First thing you want to do when you get into the patent world is check the patent at this website, type in the number, and that will tell you if the patent is still valid. Someone may have abandoned it, they didn't pay the fees, maybe it was rejected. So before you get worried that, oh my goodness, my scaffold is already covered in this patent from 3 years ago, check here because you might find it's been abandoned. So these are the types of things that go into patent law. When do things get litigated? Because these kinds of things are often context dependent and up for argument. So we could teach, I think you could teach an entire class with 24 lectures just on patent law. But that's your 5-minute introduction to patent law. It's certainly, in this box here, is much more than I knew when I was a student. So hopefully some of it is helpful to you. Okay, with that, let's move on to the next case study, which is this interesting fluorinated naphthyridine. So it's got a methyl group there, which you can imagine disconnecting immediately. You could imagine going to this compound, or you could imagine disconnecting this through directly incorporating the methyl from the beginning. So, Gigi, got any thoughts for us on a disconnection that might be good for this naphthyridine? And what would you like to put in its place? And do some sort of annulation of the type we've just done? Okay. Certainly reasonable. How do we make that?
Can we buy that?
You may go, I mean, it's certainly a good place to go sci-findering. But that fluoropyridine might be pretty expensive. Possible. Or maybe not. We could imagine this possibly comes from this. So you would sci-finder the amine, you would sci-finder the nitro compound, you would even sci-finder the ester. All of those you would look for. So nothing really immediately apparently wrong with that. Although I reserve the right to say it's bad later on, like I did with that other route. But so far it looks fine. What if we go the opposite way, where we take a ring A pyridine and we try to annulate on a ring B?
Can we do exactly the same route as in the previous case, just to take amine pyridine and aldehyde with monofluoro and acetic ester, which is commercially available?
Why don't we first go here before we get to what you're saying, Pavel? That's a good idea. You can imagine that could be converted into a triplet or bromide, and then that bromide could be then converted to the methyl group. And this may arise from So you can take this chloronitropyridine and you can react it with this tin reagent. Believe it or not, they did this on 10 kilogram scale. They have 5 different routes in this OPRD paper. We're just going to cover a couple of them. So one route that was viable was doing a Stille coupling here, followed by select fluorination of the enol ether, then reacting that with DMF-DMA, reducing the nitro, and then in situ turned into the quinolone, which they could then append on the methyl. Another possible route would just be to take this compound and say, it should be possible that we could deprotonate this position. And indeed, just LDA and methyl iodide will get you there. And then we need to think about ways of making that. By the way, another way to make this compound would be from here, if I draw this in another tautomeric form. So if you don't want to do the tin and Stille, you can take this compound and treat it with F2 gas. They did it. Multiple kilogram scale. Again, not ideal. It would never happen in this country in probably at all. This was done in Switzerland. But there are companies that specialize in using F2 gas, so they got good regiochemistry here. Good regioselectivity. Probably select fluor would work fine for medchem. That was your question, Vince? Yeah. Probably select fluor would work fine, but they did F2. Because select fluor, you don't want to do that on kilo scale. It's just too expensive. F2 is cheap if you can deal with it safely. Okay, back to this one. So here's where sci-findering helped them. That's apparently cheap, and available. So the logic tree that a process chemist will use in the so-called ideation phase of a design is come up with 10 different disconnections. Some of them will require going to the hood and seeing, do they actually work? Some of them are reliant upon this compound happens to be super duper available, and then going from there. And if this compound is super available and super cheap, the first thing you do is figure out, well, there's one chlorine I don't need. Can I get rid of that? And empirically, they found that they could just remove this through transfer hydrogenation selectively, and it's gone, leaving the other chlorine in place. Don't know why. That's just what they found. But during the ideation process, you would write this down. You would say, hey, folks, we've got this compound, very cheap. How can we convert it to the product? That's what they did.
Do you remember what the mill was offhand?
What? So remember
What the mill was?
The TAs will find it and tell us momentarily. You can then process this through a Heck reaction. So a courteous rearrangement would convert the acid to the amine, followed by a Heck reaction on that chloro, and that will then dutifully cyclize into this product by treating it with acetic acid and catalytic tributylphosphine. What's the catalytic tributylphosphine there for? Elena, any thoughts there?
That's gonna first do the Michael and then be eliminated, right?
Awesome. So that the tributylphosphine would do a Michael here, help us to get the geometry here is wrong for cyclization. So once I add the phosphine, adds in here, cyclizes, the phosphine goes out. That's why you only need catalytic. It's like a Baylis-Hillman type thing. Great. There's even more routes for this one. We could draw another 3. If you're interested, this OPRD paper, which is referenced on the front page of your handout, is a really good read. But naphthyridines are crazy complicated. So this is a team of many, many people working for a few years, coming up with 5 or 6 different routes. Okay, great. We've got 15 minutes to cover that entire board over there. That's going to require some movement on my part. So the first one here. In the 1/8 series, you've got a phthalimide protecting that C2 amine, so we can just simplify that directly to that.
Shift the camera.
Diaminopyridine, thank you, Saul. Turns out, when you take diaminopyridine and you react it with malic acid, H2SO4 goes once and only once to give us OH here. High yield. POCl3 that. And then you're done. Perfect. Next one. We've got A and B. Let's think about both. If I make the disconnection of going from A to B, I probably need something that looks like that, perhaps. Would cyclize. And this just comes back from that. Sonogashira, imine formation, and pick your favorite copper catalyst. Anything will just snap its shut for you. Let's go the other way. The other way would simply require that. Just 4-aminopyridine. And then we annulate on, and then maybe a POCl3 step, and then reduce. Or scrap it and hope for the best. Right? Scrap would get you there. And those are the two things you would draw. This one, sorry? A sort of Goreshi-Thorpe, exactly. Perfect. These are not so bad, are they? Okay, we've got 1-8. We've got 1-6. Let's move to 1-7. And we want to do medchem versus process. So if we were in medchem, probably the ideal disconnection for this, if we wanted crazy diversification scheme on those two substituents, would be what? Dihalo, exactly. So the dihalo equivalent we're going to be looking for is that. And we will do a Negishi first. Here, and a Suzuki second there. Where does this thing come from? This disconnection is kind of important because we may see it 3 more times today. Comes from this. This is a really useful disconnection to remember. So they do a Sandmeyer to convert the NH2 to the O triflate. Copper and sodium triflate will do that. And this compound comes from something you can probably predict back from lecture number 1. What did we say to think about every time you have a carbon with an amino there?
Nitro.
Yes. So that gets us back to a dinitrile. Treat this with HBr. The more electrophilic cyanide is here. So Br minus adds in here, then adds in there, and you get out that product. And this comes from this cheap material. Benzylic bromination, sodium cyanide, HBr, Sandmeyer, Negishi Suzuki, done. Now, obviously, the process chemists don't want to do this. But this route is a medicinal chemist's dream. Patrick, wouldn't you say? I can give this to the library group and have them do 5,000 Negishis, 5,000 Suzukis, and pretty much next week my SAR will be done. Now, the process route is really garbage for that purpose. Aha! So what we want to be thinking about for this one is somehow you just put R there, AR here. Bless you. This is what you're talking about, Saul? That's great. It's not quite what they did. Surprisingly, they actually used in the forward route this compound. And they can deprotonate this methyl guided by this amide. They can then quench it with, take a look at this, the diacid, acid ester, trans. The addition doesn't take place at the acid, it takes place at the ester. And that gives you your R group here. Which they can then cyclize, POCO3, Suzuki. They actually use the Suzuki on scale. But I like solids disconnection better. I'm sure they thought about it.
Does that say NHTBB?
Yeah, NHT butyl.
Oh.
Great. How about the 2,7 series up here? Can we do something super quick?
POCl3 on pyridone.
Yes. POCl3 on to give us the pyridone. So let's make that first disconnection. So Max has found a hidden Goreshi-Thorpe hiding in the weeds of the molecule. So POCl3 will get us that. And how do we make that thing? Now this is not going to work, is it? Max. But you know what will work? Aha! And then just aromatize. So sometimes, and I see this a lot, making naphthyridines, you can sneakily do them from the pyridone, pyperidone, sorry. This is a pyperidone. This is dirt cheap. You then put what you want here. So if I wanted to put methyl, let's imagine I want a methyl. I just make the methyl ketone. Easy. Let's say I want an aryl. I just make the aryl. I can put anything I want. Goreshi-Thorpe it, and then palladium heat, DDQ, MnO2, whatever your favorite oxidant is. Just put O with brackets in between. We'll get what you mean. Pavel?
What about reduced-selectivity aldehyde with monoads?
So I just write this in an equivalent. You would go and you would say, oh, I need that. Then you're good. A quick answer for this one.
Pyridone. And then take it back to 4-methyl purity. And then you can just condense that onto. Yeah, so do that, and that is like a hidden interrupted Wolf arrangement. So you can take that to the isonitrile. And then that goes back to 4-methyl purity. If you alkylate 4-methyl purity with just an alpha beta unsaturated ketone with the F-oxide leading group, and then treat that like sodium azide.
I believe this is what you were saying.
Yes, yeah.
Looks good to me. Does everybody see this? This comes from a courteous rearrangement. That comes from a super easily deprotonatable carbon. Deprotonate, acylate, courteous, and then treat with PPA or some acid, and it'll just do Friedel-Crafts, and you'll get out the product. That looks pretty good. Another way to do this would just be to start from the cyanomethyl. And because this is super duper acidic, you could easily append on, in Research style, that. Close it, and then PLCl3 it. Just treat it with acid and then POCl3, because you'll get the pyridone product. Either of these disconnections is pretty good. I know I'm moving quick, but we only got 5 minutes. How about this one? Same logic we saw before. You can look at this and say, wait a minute, this could probably come from some sort of Sonegashira event. So we can disconnect to this. I'm just going to abbreviate it as AR for now. And look what happens, folks. and that just comes from the ortho. This just comes just like we saw before. Done. Home stretch. We might be able to make it in time. This one we just saw, didn't we? Look, this is the same here. I just moved the nitrogen around. When you see this array, first thing you want to think about, dinitrile. HBr. Where does this thing come from? Super easy. Bromination with MBS. Sodium cyanide. HBr. Done. And this last one's fairly straightforward because we've seen almost the same exact thing before. You may say, hey, why is he showing us the same darn thing again? It's not quite the same darn thing because I moved the nitrogen around. But can I use the same exact logic here that I just used over there? Point of this is that some of these naphthyridines have degenerate retrosynthetic analyses. So the strategies you use for 1,7 can often be used for 2,6 as well. So this one can come back from the quasi-medchem route. That we just learned 5 minutes ago. Or it can come from the quasi-process route that Saul taught us a few minutes ago. Where I acylate here, close, or I do a cross-coupling here, and then in this case, do a Buchwald or a simple SNAR there. And look at that. We actually finished a minute early. So we have a minute. Are there any questions? Problem, Dave, with the...
It was palladium.
Oh, palladium transfer hydrogenation to get rid of that chlorine. Thanks, David. Any questions about the midterm? You guys just, take the weekend to... I guess the best way to prepare, if it was me, would be to take the parts that I'm least comfortable with and write it down. Because the rules of engagement of the midterm are you can bring anything you wrote down. So if you want to take the Jewell and Mills book and write it verbatim on a piece of paper, you can do that. So study, and the things that you're super comfortable with, why are you going to write those down? Write down a cheat sheet of these are the things I just don't remember, I don't understand, I'm not going to remember this stuff. Write it down. Bring it with you. What else are they allowed to bring? The what? Handwritten, and what else? And the essentials. That the four the laminated sheets? Wow, that's pretty awesome. And anything else? That's it. And we'll take care of you. We got Gatorade, energy drinks, snacks. Yeah. All right. We'll see you on Monday.
Please, the problem set on the desk there.
Oh, yeah, sorry. I'm just going to take this. Yeah.
Yes, sir. Introduction. It's not as actually nice to listen. How's it going?
I think it's great that you feel it. Why not?
Yeah, because I think like
We're going to see this actually after midterm in a different context, the same type of disconnection. So good you introduced it. Yeah, no, that's great.
class round 2 going? How's class
last round 2 going? Really good.
So up to Heterocyclic veteran, do you feel like you actually understand it now?
Yeah, I understand everything.
Are you gonna take an exam with them? Huh? Are you gonna take an exam with them?
Oh, that's pretty well.
That's what she said.
Nice. Oh, maybe. What day is it on?
Huh? Monday.
And that's how long?
5, 6, 4 hours.
Yeah, I'd probably be pretty mad at me.
What happened to your paper? Have you gotten a review back?
For my first paper?
Yeah.
We're going to resubmit soon.
To
We have
Jack?
to restructure the manuscript.
To Jack's?
To Nature Camp.
Nature. Wait, where did you guys submit it first? I saw you.
Nature.
Oh, Nature.
To Nature Camp.
Oh, okay.
And Nature Camp's like,
Go to science. You will be quick anyway.
dude, it's not going to get into science.
No, just try it.
It's so boring.
Nature Camp takes forever, though.
Huh?
Nature Camp takes forever. Oh.
I don't really care when it comes out.
Sure.
I guess that's true. It will be coming out, yeah.
Do we not hold on to metallics today?
No. I don't know if we really have to erase it.
You being nice?
Yeah.
Oh.
Such good handwriting. How's TAing going?
Dude, it's fucking brutal. Yeah.
Is it brutal?
So much work.
Yeah?
So fucking busy, man.
It's like any time in the day when you're like, oh, like, I'm gonna do this. And then you're like, fuck, no, I have like 100 TA things to do. Wow. Yeah, it's pretty bad.
And then 30 minutes before lecture, it's like, hey guys, could you look it up? Could you have a literature for this?
Yeah,
Should I
even though I've
put
been
it back up?
even though I've been teaching it for the last,
Yeah.
that exact way for the last like 6 years. You guys are doing so well.
Oh well, oh well.
This is such a good class. Oh shit, are these their homework?
Yeah.
Is that due today?
Yeah.
Wow.
Just suckers, recycles.
Oh, they got that one right.
You hope so. Can be.
Check B.
I'm sure everyone just repeat it up. Do you want me to keep this? I guess I can.
Sure.
Do you wanna go to secret session after getting food?
Yeah.
And pee. Yeah, I'll be in my office.